Hey everybody, this is your 3-3 calculus video on differentiation rules. So we used some of these rules informally on 3-2 and I showed you like what shortcuts you can take. And in this video, we formally defined them. Now just as a reminder, on 3-2 we had some copy paste hints on the calculator. So for example, if we got point and some decimal and then 499, even if you had some numbers after it, you just ignore those extra numbers and make it whatever the front was and then a 5. If you see at least 3 9s in a row, then just stop and make that 5. And then on this one, if you have 0.0123123, make sure it keeps on going to the middle of the screen and then convert to the fraction. Then to the fraction. And on this one, if you have 0.0125125, then all of a sudden it says 13. That's wrong. That 3 is a rounded number from the 25. So what you're supposed to do is say 0.0125, 125, 125, 125, and then convert it to a fraction. So as a reminder, like on the copy paste part, we did it like this. You go to the calculate part. Let's just say we have one of our functions like 3 minus x to the third plus x squared. Whoops, I need to make this there. Plus x squared. If we just have some random curve, and if we do analyze, then dy dx, which was number 5, you can type in your position number, like position 2, and this gave me the answer. If I change it to more like one where we have to get a minimum, I'll make this a plus. Let me get to the example we used in 3-2. Okay, it was actually in 3-1. Where at one time I had 1.4999, and so I made that 1.5. And then you got to convert your other decimal, like in this case, negative 8.75 to negative 35/4. But it was 3-2 when we had a bunch of calculator steps. Like on this particular one, where I had 0.0925, 925, 925, and then it said 93. So we had to cross that 3 out, make it an extra 25, interpret it like 0.0 with a 925 repeating, and that's 5 over 54. So that's kind of like what I was reviewing right there on how we did that. So again, if you need that one more time, let's go to 5 over the square root 11 minus x, press enter. And then in my case, I'm doing position 2. And so I go menu 5, well 6 then 5. Position 2 gives me this number. And again, we had to like move the little mouse over here, click it. Now it's dark blue, click it again, and it's like that, where you can actually hit copy. So Control C, and then go to the calculate screen, go to Control V, and then change this to 2.5. Now, even right there, it's not long enough because it has to go like halfway. Because see, if I just do that, that's an ugly fraction that we don't want. But if you go back to that and then put some extra 925s, then it's going to work. Then it's 5 over 54. Okay, so hope that helps with that part. Now let's move on to 5-3 or 3-3. So on 3-3, we are doing derivative calculations with the first and the second derivative. So think of if we start with y equal x cubed without anything, just as a really basic example, then y prime would be 3x squared and y double prime would be 6x. So what we're doing is we're taking our exponent times the coefficient each time. And so you're at this level, x cubed, then you're at the x squared level, and then at the x level. You're going lower in power, which is what the derivative is about. Later on, much later actually, you'll do integrals, and that's when you're going to go backwards, when you're going to go from x to x squared to x cubed. Okay, so again, why we're studying this, previously we used a few shortcuts on taking derivatives, and when it was not available to use limits. This section formally introduces rules that allow us to differentiate constant functions, which are just numbers, power functions, polynomials, rational functions, and certain combinations of them, then to simplify and directly without having to take limits each time. In other words, I know this year on 3-2 we didn't really even have to do some limits for the derivatives. We just did limits on chapter 2. But if you didn't know how to do the shortcuts and if you just use view and example, then you probably follow the process with taking limits, which takes longer. So now we're talking about powers, multiples, sums, and differences. A basic rule of differentiation is that the derivative of every constant function is 0. So that means if you're taking the derivative of 5, that'd be 0. Any number, you would get 0. So the derivative of the constant function formally says if f has the constant value f of x equals c, then df dx is also renamed to be d dx with respect to c, with c plugged in, and that is 0. Now you also have what they call derivative of a positive integer power. So if n is a positive integer and you're taking the derivative of x to the n, then that would be nx to the n minus 1. So basically we take our exponent, put that as our coefficient, and decrease the power. Now in this definition, they don't say to take the derivative of x, which is 1. So that's fine because it is just 1, but there's another rule that makes you go one more step. So that basically means multiply your exponent by the constant in front of x, or you can think 1, and decrease your power by 1. So if you have x cubed plus 2x, then that 3 comes in front, and that becomes 3x squared, because we went down by 1, and because it was 2x, that just became 2. Now you have your power rule general version, which is related to that. It says if n is any real number, then the derivative of x to the n is n times x to the n minus 1. Now we are going to have to do some u and v notation, which is harder, which is why it's split up into 3.3, being separate from 3.2. The functions we're working with need a differentiation formula, and they're likely to be denoted by letters like f and g. We don't want to use the same letters as them, with your general differentiation rules. And so instead we use U and V instead of F and G. So what you'll see, for example, is you say you have some numerator function and they're going to call it U, some denominator function and they're going to call it V. Now that's going to be like on the next page. And also, like, say you have some function here that's U and you're going to be multiplying it by some function here which is called V. So this one you'd have to use the product rule, and this one you'd have to use the quotient rule. And we'll define those in a moment. Basically, you can think quotient is going to involve subtraction, product rule is going to involve addition. So before we actually get to that, we have the derivative constant multiple rule, where say you had a number like 5x where the CU is, then you'd have to take your your 5 and put it in front, and then you have the derivative of whatever the u is. Now in my case I just have x, and so the derivative of that is 1. But we'll do some harder examples in a little bit. Now there's also a derivative sum rule, which means if u and v are differentiable functions, then their sum is differentiable at every point where they're both differentiable. And so if you have u plus v in parentheses for the derivative, then you take the derivative with respect to x of u and of v, and just add the answers. Now here's the product rule, which again we used a little bit on 3.2. If you have the derivative of uv, then that's going to be u times the derivative of v, which is like u times v prime, plus, this time they're doing the derivative of u, so that's u prime times v. The order doesn't matter. You could have said u v prime plus v u prime. The order doesn't matter. You could have even put v prime u, plus u prime v. So those are just a few examples. The order doesn't matter. Now on the quotient rule, we're basically going to have, like, let's just say x squared plus 1 over x cubed plus 2x. We're going to name this u, name this v, and we have to go with the v u prime minus u v prime over v squared. So whenever we use the quotient rule, order does matter. Because it's subtraction, it's not addition. So the top one was order doesn't matter since it's addition. And this one, order does matter since it's subtraction. Okay, so over here we say if y equal f of x is a differentiable function, then f prime is the derivative. And then we also are talking about getting the second derivative. If we differentiate f prime, then we get f double prime. So f double prime is f prime prime. It's called the second derivative because it's the derivative of the first. Now I do remember some problems making you get the derivative as far as you can, and once you get to that, like, the derivative would always be 0 at the very end on that particular problem. But I'll show you an example. But you could start with like x to the 5th, and then the derivative, I'm going to call that f. F prime would be 5x to the 4th. F double prime would be 20x cubed. F triple prime would be 60x squared. f to the 4th power, you could probably say IV equal 120x, and f to the 5th would be 120. So then f to the 6th or higher would be 0. So after you get to this point, it's always going to be 0. I don't care about, if you're talking about the 100th derivative, it's 0. Okay, and then here's just your other ways to write it, but I always just use f double. So y prime is that one, y double prime is that one. D squared y over dx squared is how we read that. And then this is y triple prime. This is called y super n, but I never really say super. And then there's d to the n of y by dx to the n. And this is just d to the n. Okay, so that's the actual notes for it. Now we just put it into practice. So there's actually no work to do on this. You have 7t to the 5th minus 5t to the 7th. What you do is you take this and multiply. So 5 times 7 to the t, well, times t to the 5 minus 1. There, I made work. So then that'd be 35t to the 4th. And then on this one, we've got negative 5 times 7 is negative, well, minus 5 times 7, and then t to the 7 minus 1. So we can say minus 35 t to the 6th. And so you can see that that's what we get for there. Just be careful about what variable you're using, because obviously it's not always x. And so use whatever variable is in the problem. Use the variable in the problem. And then for the second derivative, we do 4 times 35 t to the 3rd. So that's 140 t to the 3rd. And then we have minus 35 times 6 is 210. So minus 210 t to the 5th. So there's that answer. Now, on one like this, it's a divide by 4, and so you might want to make it as 9 fourths x to the 4th minus 7x. Now, sometimes what you'll notice is they put the denominator and the exponent the same to show you the case where all they do is cancel out. So you say 4 times 9 to the 4th, which is really just 9, and then lower by a power so you get x cubed. So that's 9x cubed. And this part, you're just saying the 1 is invisible. We never write that. This would be minus 7 times 1, x to the 1 minus 1. So this is 7x to the 0. Well, we never write x to the 0 because x to the 0 is 1. So that's just 9x cubed minus 7. So that's what you get there. And now we're going to just go 3 times 9 x squared, so 27x squared. And then the derivative of negative 7 would be 0. So we just write 27x squared. So that's how you do those. Now on this one, they kind of have it mixed where one of them was a negative exponent, which means 7 over x to the 5th, but we don't really want it that way. And then this one is in the form negative 6 over x. Now, I could have written that as minus 6x to the negative 1. In fact, I'm going to do that larger over here. So that's our original y. So for y prime, we do 7 times negative 5, which is negative 35. And now we're lowering by power, so that's x to the minus 6. And then what that really is negative 35 over x to the 6th, because you can move it. Now on this one, you could say negative 6 times negative 1 is plus 6, and then lower it by 1. So that'd be plus 6 over x squared. So that's how you get these. Now, when it comes to taking the second derivative, use this form for the second derivative, because it's going to be easier for you from my experience. Because then you can say, I'm going to do negative 35 times negative 6, and then I'm going to make it x to the negative 7. To me, it's easier to get from that step than this step. Then on this one, we're going to do 6 times negative 2, x to the negative 3. So when we multiply those numbers, we get 210 x to the negative 7, which is 210 over x to the 7th, and then minus 12x to the negative 3. So negative 12 over x cubed, and that's your answer. Okay, now on this one, this one's like easy. 5x squared, so you do 2 times 5, and then put x. And this one would just be minus 10, and this would be plus 27x to the negative 4. And they kept it that way, which is great, instead of putting it as a fraction, because again, now you're doing this one. I don't know why they're inconsistent, but I like this way better. It's probably one of those things where in Math Excel they would accept either answer, like this one or this one, and this one or this one, but I can't say for sure. I'm just working towards the paper answer. So you can try that out and see how it works. But I know for sure, how to get it with the paper answer. Then now that we have 10x, that'd just be 10. If you take the derivative of negative 10, that'd be 0. And on this part, you do 27 times negative 4, x to the negative 5. And the 27 times negative 4 is negative 108. Okay, so on this one, if you want to, you could make that 3s to the negative 2. Wait, I'm sorry, I meant 1/3, I think. Okay, let me just think for a second. Yeah, so then we would have it as negative 2 times 1/3 s to the negative 3, which turns into negative 2 over 3s cubed. So that is what we want for the first part, or first term. For the second term, we'd make this minus 8 over 5s to the 4th. And so that would be like, let me write this a little bit better. Minus 8/5 s to the minus 4 And then when you're doing your derivative, you take -8/5 times -4 and then lower it by power to the -5. And a -8 times a -4 is +32, and then over 5. And then if we have s to the -5, that'd be s to the 5th. So then you just put those together. So that kind of groups together like that. Let me write that better. -2 over 3s squared plus 32 over 5s to the 5th. So that's your answer. Okay, now we want to go one more level. So if we want to think of that as, whoops, I put squared here and that was cubed. Couldn't read my own writing. If we want to think of this as -2 thirds s to the -3 plus 32 fifths s to the -5, then this would end up being -2 thirds times -3 s to the -4 plus 32 fifths times -5 s to the -6. And you see your 3's cancel and your negatives cancel, so you get -2 s to the -4, which means wait, was I supposed negative times a negative is a positive. Sorry about that. So then 2 over s to the 4th. And then this is a positive times a negative, which is a negative. Your 5's cancel. And so 32 s to the -6. So this is minus 32 over s to the 6. And so that's that answer. I'm going to stop right there for that video because I need to work on the quotient rule in a different video, because I know y'all have not seen the quotient rule yet on 3-2 that often. I'm just going to do that in a different video. Okay, hope that helps.